Yay, I think that's my first question. Kat, can you confirm if you can actually hear what I'm saying? Sorry, I'm just doing a little bit of troubleshooting. Kat, can you confirm that you can hear my microphone? Can you hear what I'm saying? Excellent. Okay, so the difference between gravitational potential and gravitational potential energy. In the same, yay, there's more people here. I'm so happy. Okay, in the same way that, let's compare fields and let's compare force. So I think we all have a fairly good grasp. I should probably come up with a new worksheet to work on this. But we have fields and we have force. And when we measure gravitational fields, we would measure it in newtons per coulomb. So it's essentially newtons per kilogram. We're going back to gravity. Because remember that these ones had mass and these ones had m1 and m2. So if we take our force and we divide by the mass, then that's giving us what our field is. And that's why we can measure it in newtons per coulomb. Newtons per kilogram. And so hopefully we have a good understanding of that. So essentially if the gravitational field strength is 9.8 newtons per kilogram, for every kilogram that I put in that space, there will be 9.8 newtons of force. Well, the exact same comparison can be made with potential and potential energy. So if the field is how much force there is for every kilogram, potential is how much potential energy there'll be for every kilogram. So when we're talking about gravitational potential energy, we would measure it in joules per kilogram. So how many joules of potential energy you're going to have for every single kilogram that I put at that location. Does that make sense? I know there's about a 20-second delay or so from what I say and what I write to what you're seeing. Hopefully it's not the full 20 seconds. I tried to change my settings to make it as quick as possible. Okay, excellent. Who else has another question? And by the way, feel free to line up the questions a few seconds. You know, if you have a number of questions, you can type them all down and we can just go through them in order. Yes, Kat, it will be. So actually the lag is not too bad. I think it's only about 3 or 4 seconds. So does anyone have any questions? Or B. Excellent. Okay. So this is the question here. High voltage supply unit connected across parallel plates. Separation is 50 millimeters. So let's draw this out first of all. So these are our parallel plates. The difference here is 50 times 10 to the minus 3 meters. That's our space between them. and the voltage or the potential difference is 4.5 kilovolts. So it doesn't matter necessarily how we're, what values the plates have. The difference is, the important point is what the difference is. So if we say that this is 4.5 kilovolts, we can say this is 0 volts, or I'm just going to change that to 4,500 volts. But likewise, this could be, say, 2250, and let's do a different color. It could be 2250 and negative 2250, because that would still give the same difference as 4,500. So just as a small side point there, all that matters really is the difference between those two plates. Okay, so if we want to know the electric field between the two plates, we know from looking at our square, this is our field, this is our potential. To get from here to here, we would need to divide by the distance. Remember, when we're talking about radial points, these ones are over r, and these ones are over r squared. So even though we're not talking about a point charge, we're talking about plates, the idea that you need to divide by d, or divide by r, to get from potential to fields, that is still correct. So in this case here, our formula for E is just going to be V divided by D, which is going to be 4,500 divided by 50 times 10 to the minus 3, which gives us this answer here, 9 times 10 to the 4 volts per meter. Okay, so that's the first part. Now for part B, what is the force on a droplet in the field that carries a charge of this? So now we look back at our square, and we know that these ones are with, sorry, not M now, I'm getting confused. This is Q, this is Q1, Q2. So in order for me to go from field to force, mathematically, what do I need to do? Well, hopefully you can see that if I'm going from Q to Q1, Q2, I'm going to have to multiply by Q to get this, or likewise I can divide by Q to get that. So if I want to know what my force is, F is going to be Q times E. The Q itself is this 80 times 10 to the minus 19 coulombs, and the E we've got from the first value is this. So in this case here, it will be 80 times 10 to the negative 19 multiplied by 9 times 10 to the 4, and that's going to give us this value here, 7.2 times 10 to the minus 13. Good deal? Okay. Is that, I'm not sure who Anim is. Anyways, so that second question there, okay, we'll do question 6 in a bit, thank you. So the symbol for gravitational fields versus forces is still the same as we have here. So E and F, and the symbols are the same whether we're talking about gravity or we're talking about electrostatics. It's still going to be, so E on the left-hand side, F on the right-hand side. Those are the same symbols whether we're talking about electrostatics or whether we're talking about gravitation. Same symbols. This makes it hopefully less confusing. Prior, no questions. Okay, thank you. So how to solve question 6. So a certain gas in a tube subject to an electric field of increasing strength, the gas becomes conducting when it reaches 35 kilovolts per meter. And 35 kilovolts per meter is roughly the same field strength that you need to have a lightning strike. So in the air, if you have a difference of 35,000 volts separated by a meter, you'll get a lightning strike. So if you think about how high clouds are, you have to have a huge potential difference. If it's like 1,000 meters, then you need to have 1,000 times 35,000. So 35 million volts might be the difference between a cloud and the ground, for example, in order to have a lightning strike. So just a little side note. Okay, the electrodes are 84 millimeters apart. You assume that its electric field is constant. So what's the potential difference between electrodes that is necessary to produce an electric field strength? So what this is saying here is we know that if our E equals 35,000 volts per meter. That's our E. We also know our D, our distance, is this 84 millimeters. So if we go back to our square, we're going from potential to fields, and we're trying to solve, sorry, I did that sideways. We're trying to solve the potential difference. So what we're trying to find is, we know V is going to be, so to go from V to E, we need to divide by distance or multiply by distance. So V is going to be E times D, just like E is V divided by D. I've just rearranged this here. So this would be 35,000 volts per meter multiplied by 84 times 10 to the minus 3 meters, and that gives us this value here. So 2.9 kilovolts, or 2,900 volts. So that's our first part for question 6A. For question 6B, if we want to know the force, well, we now know the field strength is this, and we are trying to find the force, and it's on an electron. So this is the one hint that's often going to be in a question, is they're not going to give you the charge, they're just going to say that it's an electron. And so from that, we need to recognize that Q of an electron is 1.6 times 10 to the negative 19 coulombs. So it's often just going to be given to you as a value, and not necessarily, or given to you as a fact that it's an electron, and not that it's the charge given. And so now if we think about this, if we want to go from E to F, we would need to multiply by Q. So F equals E times Q, so F for part B is going to equal 35,000. Instead of using volts per meter, because it's the same unit, one thing that you can change if it makes it a bit makes it make a bit more sense is you can say this is newtons per coulomb, and then we're going to multiply that by 1.6 times 10 to the negative 19 coulombs, and that will give us this value here, 5.6 times 10 to the negative 15 newtons, if you multiply those together. Hopefully that makes sense. And lastly, for part C, why does it become conducting only when the electric field strength reaches a certain value? So this is a question that I don't expect you to be able to know off the top of your head. It's more of a thinking question. So if you have an atom, let's call this just a neon gas molecule. If there's no electric field, this is going to be uniform. So the electron cloud that forms around the proton will be uniform. It will be evenly spaced out. Now, if all of a sudden I add an electric field, so let's say I have a positive plate here and a negative plate here, we know there's going to be field lines that go in this direction here. And we also know that in this atom, so I'm going to redraw this atom just below here, in the atom we know that the negative electron cloud is going to be attracted towards the positive, and the positive proton is going to be attracted towards the negative plate. And so what's going to happen is we increase the field, our atom is going to look a bit more like this. So you're going to have the proton kind of a little bit more to the right, the electrons a little bit more to the left. And so if we keep applying a stronger and stronger and stronger field, eventually this proton, or one of these electrons, will just be ripped away from the atom entirely. And so as the electron gets ripped away, that's when you get ionization. So now if you think about the situation afterwards, you're going to have this negative charge that's going to be moving in this direction. You're going to have a positively charged ion. So it's positively charged because it's missing an electron. That's going to be moving this way. And essentially that is a current. So if we have negative charges moving to the left, positive charges moving to the right, that's the same thing as a current. If you take chemistry, you may have seen this with electrolysis, where if you put, for example, a positive and a negative probe into salt water, you might have sodium going towards one electron, chlorine going towards the other probe, or the other positively charged probe there. So the same kind of thing happens with charged gases. This is how a neon light works. You plug in a neon light, it puts a huge potential difference in here. The electrons start moving towards the positive end, the positively charged ions start moving towards the negatively charged end, and that allows a current to flow, so it allows the light to continue. Okay, example 2. So if anything was not clear, just let me know about that explanation. Okay, charged particle, electric field, charged metal surface, force is going to be that. So you want to know what the charge is going to be. Okay, so we know, again, going back to the square, F is going to be the charge of an electron, charge of a particle multiplied by E, and so the charge is going to be F over E. And that, in this case, gives us this value here. 1.3 times 10 to the minus 7 coulombs is going to be our amount of charge on this dust particle. So whether it's positive or negative, what you are thinking here, okay, so the, let's see. Charged metal surface. Okay, I'm just trying to draw this out here. So we've got a charged metal surface, and electric field is 65,000 volts per meter. And so whenever you have a positive charge, if we think about like a metal sphere, let's say this is like a metal sphere, we know the field lines always point away from it because the field lines represent the direction of force on a positive particle. So if I put a positive particle here, it's going to move to the right. If I put a positive particle here, it's going to move away from it. So in this case here, the force due to the field strength is 65. If it's a positive value, positive means away from. So we'd call this a positive field value because it's moving away from the charged sphere. So that means that for this metal object here, the field is moving away from it because it's positive. Now the force is going to be towards the metal surface. So our force is going in this direction here. So what does that tell us about the charge on that particle? Well, we know that the field lines tell us a positive charge would be repelled, and so the positive charge would be repelled, and this charge is going towards it, then this charge must be negative. Does that answer your question for question 2? Hopefully it does. Is there a key for this worksheet? No, I haven't made a key. I've just put the answers here for you. So I want you to try and work them out for yourselves. And then if you're still stuck with a problem, that's what these tutorial sessions are for. Or, of course, you can email me. Hopefully these are a good option. Any other questions that anyone has? Number 5, sure, Claire. I have to say, I really miss having students in my class. So it's nice. I kind of feel like you're almost here with me. This is nice. Okay, so hopefully everyone's doing okay in the midst of this craziness. So let's try number 5. Now we have the same potential difference. So in this case here, this is the potential difference, and we've now changed the space between these plates. So this is no longer 50 millimeters, and we're trying to, this should say, by the way, this is a typo, this should say it is now acted on by a force of 4.5 times 10 to the minus 14. Hopefully that wasn't what's causing the confusion. Nonetheless, if we have this thing here, we are looking for the new separation. So we need to find this D. So that's what we're trying to find here. What is D? And we also know that the force is 4.5 times 10 to the minus 14 newtons. And we know that the potential is going to be 4,500 volts. And so if we look back at the square over here, we have this. We have the force, and we also have the potential. Now, we also know that it is the same droplet. So the droplet has this charge here. So we also know Q is 80 times 10 to the minus 19 coulombs. So We know F down here. We don't know E, but we do know F and Q. So hopefully we can see that if we know F and Q, we could find E. So I would definitely encourage you to try it out for yourself. If we know F and Q, we can find E. If we know E and V, then we can find D. So if you're feeling stuck, try drawing out the square and seeing what you come up with. So if I want to go to find E, E is going to be F divided by Q, because we know that F is E times Q, so that means E is F divided by Q. So that's what we have there. So this is going to be 4.5 times 10 to the minus 14 divided by 80 times 10 to the minus 19. So what do we have here? 4,500, oh sorry, that is 4.5 times 10 to the minus 14 divided by 80 times 10 to the minus 19. That gives me this is as my field. So my field is 5,625, and this is going to be measured in volts per meter. So this is going to be V divided by D, and therefore D equals V divided by E, which is going to be 4,500 divided by 5,625, and that equals this value here, 0.8 meters. Sorry, we had a technical difficulty there. Okay, hopefully we got to the end of question 5 there. I'm not sure, I just had the screen go blank for me, not sure if it went blank for you. Okay, and the next question, is there an updated formula sheet? Yes, there is. If you, actually, you know what, I'll just post it onto the I'll post it into Google Classroom. But it's the same one we were using in class before, the one that we got printed out, but I'll post it to Google Classroom. So there is going to be a formula sheet, but again, the formula sheet is going to be limited in terms of the number of formulas it has. Honestly, I would genuinely say that if you understand how the square works with these 4 quantities that I'm just drawing on the bottom right-hand corner, if you understand these 4 quantities and how they relate to each other, this is all the formulas that you need. You've got every formula to relate potential energy and force, potential energy and potential, potential and fields, fields and force. You've got all the questions, or all the equations in one place. So I would probably encourage you to get used to that, but I will post the formula sheet there anyways. And do we have any more questions? Okay, I'm going to take that awkward silence as meaning there are no more questions. Hopefully you found this useful, and it is something I'd like to do on a weekly basis going forward. It is really lovely to see all of you here, like I said, and feel free to email me if you have any other questions besides what we've gone over here. And yeah, keep in touch. Thanks very much. Okay, bye.